Hello, uh, welcome. My name is Steven, and the reason I'm whispering right now is because it is currently 12:40 a.m. and my roommate's sleeping. But I was gonna start this video at like 9 p.m., but we kind of just procrastinated and we talked about I think we were talking about like how cameras worked. But anyways, I've always wanted to do this, but essentially this is going to be a series of videos, or I don't know, it's like a live stream that's pre-recorded where I'm just going to try unedited implementing things, because I think the best way to learn something is to build it. And I think it could be as a blueprint for how you to go about approaching these things. So right now I want to do deep learning from scratch. I really want to get a very strong grasp of how a transformer works, how the backbone of any modern neural network model works. So Karpathy obviously has a great series of videos that you should watch if you actually want to learn. So I did watch the videos that Karpathy made. These ones, I don't know why it's not showing, but yeah, I think these are really great videos. But I think like you watch them, you sort of follow along. But then if you're asked to like re-implement it, probably forget some parts of it. So that's my goal now, is like, okay, I think I have an intuitive understanding. I followed along, but I actually want to like write it from scratch myself and sort of like figure it out. And I think we can just figure this out together. So the first goal today is to just like implement an automatic differentiation engine. So I guess like first of all, let's sort of like understand how it will the most basic feed-forward neural network works, right? So I guess like for implementing a neural network, what we're going to eventually do is test with MNIST. All right, we're gonna have like figure out some way to like download the MNIST data set. I think I can do this in like what, an hour or two. All right. So first of all, what is a neural network? A neural network consists of a bunch of these neurons, which I guess are also nodes. All right, there's a bunch of these. And they're connected via these edges. But neural networks essentially allow you to represent, I don't know, some more. They represent relationships, right, between your input and your output. So these are like this is your input layer. These are hidden layers. And then you have like some output layer, right? And we'll talk more about this in a second, but okay, this is really basic. You should, if you're watching this video, you probably know this, right? But essentially there's these edges. Now this is all like super high level and abstract, so we need to, I think the difficulty will be when we actually implement these. So all of these are connected by these edges. These edges are nothing more than just a simple multiplication, right? So imagine this is some number, a vector. Right, this could be 5, this could be 4, this could be 1, this could be 0. You multiply these numbers, and then these are all multiplied, and then here you apply, so this 4 is connected here, this 4 is connected, and then there's another number here, and then there's a number. It's all connected, so this number, what this will represent is a summation of all of these different numbers, and then you can add a bias. So it's going to be like W1, A1 plus W2, A2 plus W3, A3, etc. plus the bias, and all of that multiplied by an activation function. And how do I know this is true? I actually don't know what this is true. So what I'm going to do right now is going to pull up the deep learning book. And I think I actually have it downloaded somewhere. So let me go in my books. And then, where's deep learning? Do I have deep learning here? Humanities. Old. Nope. F-sift here. I guess I don't actually have. I don't have deep learning. Okay, I'll download it. When you're not sure, I would recommend you just look at the source of truth, which is the book. Okay, so let's go books, download. Yeah, and let's review the formulation. Singular value decomposition. Okay, I actually need to review this as well. Singular value decomposition. Okay, we're going on a little tangent here because I actually need to understand how singular value decomposition works. Oh, this is really useful. Linear algebra. Okay, we're doing a tangent on linear algebra because I actually need to understand this as might get asked about this in interviews. So scalar, okay, what is the scalar? A scalar is just some number, it's just a single number. Okay, and I'm gonna write some notes here. I mean, I know what a scalar is, but like, I think the difficulty is when it comes to like actually explaining these concepts and distilling them. Like, I guess like those who really understand a topic, they're able to explain it. Whereas if you sort of internalize a topic, but you don't know how to explain it to other people, then maybe you don't actually understand that topic, right? Like you understand what, like you can visualize what a vector is, but can you explain what a vector is? A vector, is it a series of numbers? It's a series of scalar numbers, where scalars are single numbers. So I guess a vector is a number of numbers. And then a matrix is a series of vectors, right? Okay. Yeah. So
Here's
far.
What I found.
Shut the fuck up. Oh, sorry. Scalar. I do have a note on scalars. Okay. Okay. I guess the way I defined it was has magnitude but no direction. Okay. Transpose. We know what a transpose is. Is when you flip. Transpose is when you flip the array. You flip all the indices for the I and the j, I guess, right? It's, you can imagine, visualize it as a flip alongside the diagonal, but really what's happening is the indices I and j are flipped. Okay. Called broadcasting. Okay, so I guess first thing we need to review is a matrix product, right? So I know how to do a matrix product. It's like the first row is multiplied by the first column, the second row is multiplied by the second column. But really, Cij is equal to the sum of Aik, okay, yeah, which is what I described. So here, I guess, a super quick note on a matrix product can be useful. Okay, so we have a matrix, C equals AB. The competition is given by Cij is equal to the sum K for A. So it's a row for given. So this Cij represents the ith row from A times the B, and then BKJ, I guess. So formally in words, Cij represents the multiplication between the ith and the kth from A. The dot product and the jth row from B. Okay, this is pretty self-explanatory, but I think we need, I wanted to understand singular value decomposition, but you know, this is just like good. Oh, element-wise product. Is that what you call it? Element product. Yeah, I didn't know this was a thing. Element. I knew this was a thing, but I didn't know that there was a term for it. Element-wise product. Of all between two matrices. I think numpy, this is the default behavior. And you do A times B. Element-wise product. Okay. Matrix product is matrix what are the properties of a matrix? Fundamental subset. I don't know what this is. Hmm. Did we not talk about, I don't have notes on matrix properties? A, B plus C. Okay, this is super easy. Don't waste too much time on this. Associative. A, B, C equals A. Okay. This is AX equals B is one of the most fundamental equations there is. thought I did in least squares. That's linear equations. System of linear equations. We have a set of linear equations. We can write it down as a matrix in matrix form, i.e. ax equals b, where A is a matrix. And m by n. Okay. And we have the matrix inverse. What is the matrix inverse? Does not change any vector. Okay, wait. I want to understand singular value decomposition, so don't spend too much time on this. The solution is given by x equals a minus 1. Oh wait, this is wrong. A minus 1 b. C matrix for how to compute A. This is very okay. Matrix inverse. You can okay, yeah. Okay, that's what linear dependence means. Okay. So a span is a term that I've ran across, multiple times throughout my linear algebra class. Also, okay, I've taken several linear algebra class, but I think it's been always hard to internalize a lot of these concepts. So I hope that right now me explaining this can help me internalize. So a span in my head is a set of vectors such that their linear combination, that is, a multiplication of any vectors by a constant, can generate any representable vector in that particular Subspace? See, I don't even know what a subspace is. Did they talk about subspace? Vector space? Yeah, subspace. Okay, so did you talk about subspace? Oh, there's actually quite a non-trivial amount of. This is actually great. I like that there's math behind this. Yeah, all of this is super basic. Okay, wait, I'm gonna get a drink real quick. Alright, seems that my roommate is not sleeping. Okay, it's like 1 though. Cheers. This is non-alcoholic. This is sparkling water. This is like the best sparkling water I've ever had. It's so good. Okay. Alright, so where are we? We want to solve a set of linear equations. And we're talking about span. Why are you talking about span? Equation 2.11 must have exactly one solution. Okay, this is really interesting. We can examine I have a vague recollection of this. If you can reduce down your matrix A, we learn LU factorization. There's Gaussian elimination. Sorry guys. This one's a set of all possible the column space. Column space. It all makes sense now, huh? Find a row space. Final example. Fundamental subspaces. Yes. It all goes back to the most fundamental equation ax equals b, which is a set of a system of linear equations, right? And we're interested in solving for x, right? Such that this equation is satisfied. And we can actually we can just solve for it, right? But sometimes there might exist an infinite amount of solutions for there are certain x conditions. If both x and y is then z is columns are sorry. Yeah, linear independence is that no vector in this set can be created as a linear combination of any other vectors. If it is, then you can rewrite the sum. You sum all of these vectors up, and it is equal to the zero vector, right? Because it means that at least for one of these vectors, it can be represented as a sum, which means that it is redundant. And why is this important? Because this. Square matrices. Square matrix. Okay. Okay, this part is confusing. Yes, it's unique because it's given by 1 over the determinant of it times the adjugate. Yeah, okay, inverses are unique, okay. There's only one solution because the matrix inverse is unique, but is A always invertible? That is we can first examine A. That can only happen. So A is only invertible when there is a single, when there are multiple no solutions, A cannot be invertible. Because if there was, then there would be multiple verses, which is a contradiction. If there are solutions but a matrix universe exists, that is a contradiction. Okay. Okay, so then that's why they say defining whether AX has a solution, the determinant whether B is in the span, the columns of A. Ah, I see, because essentially what you're doing is a dot product, right? You're multiplying, you can imagine, you can picture it as the first row. I guess there's multiple ways. So the way you visualize this, B, so there are two ways you can visualize AX equals B. First one, you can see it as row-wise, where each row you have a dot between A, K, J, X, K, K equal where sum of K, AK plus BK. Between the ith row of X, B of I equals sum of J, A, I, J, XJ. Yeah. Okay, you can see as a dot product, or you can see it column-wise, where you have B equals A sum of K, A, sum of AIJ, sum, what's like A, J, sum J, AJ dotted with XJ times AJ. That work? So you have the b, the vector b of I. X0 times A, 0 times A, 0 x1 times A, you see column-wise linear combination. How can you do that? You can. Hmm. Yeah, I guess it's literally just x0. Maybe a diagram was better drawing. Embed. So I guess you have two matrices. So you can see it as, so we do red, 1, 2, 3, 4. And then 1 green. Hmm. That's equal to, and it's like a bunch of dot products. just like this, where you can see and the other way is to as sound right. Hmm. The first row is like column. You see it as it's this first row times this plus the entire column. This value is equal. Also see it, this value is equal to this value times this entire only A1 plus X2 Yep, okay. Thus, you can with this way of seeing the matrix, you can see that a solution only exists when B is in this column space of A. Column space. A 3 by 2 matrix. Determining whether AX equals B has a solution thus amounts to testing whether B is in B is in this one. So in summary, we look at the column space to sort of examine, consider a system of linear equations AX equals B, and you look at the column space of A, right? So first of all, when you do AX equals B, really what this is stating, you can rewrite this as, you can think of it as a system, I guess the x's are your unknown. So you can think of AX equals B as a linear combination of the columns of A, right? So you can have x1. So if you, let's say the columns are A1, A2, A3, A4, right? A1, A2, A3, A4, then AX equals B is equal to the first column multiplied by your x1 plus your second column times your x2, and then all of that equals to B. And if you rewrite it that way, then you can kind of see that the solution x, right, is B can only be solved like this. So there can only exist a system of linear equations where this system of linear equations is satisfied when B is in the span of, when B can be written as a linear combination of A, i.e. B is in the span of A, right, by definition. And so what that means, and then if you look at if some of the columns in A are linearly redundant, like you can infer different things based on what A looks like. So like if you, and then that is equivalent redundant. All right. So if your coefficients were 2, 2, 2, 2, that column space. Why? Are the requirements? Okay. A plus b squared. Square. Dude, why am I studying this? I just wanted to know how singular value decomposition works, man. Although this is very fundamental. The fact that I don't understand this. I'll be in R of M, then the column space of A must be R. then some vectors be linearly independent. If you write down the linear combination of A and you try to solve it for B equals 0, then the only solution will be C. In the formal term. What it really means is that no vector can be written as a linear combination of other vectors. A solution exists also it's only a matrix is only invertible in its nmat. And a span of the determinant. I think I, for example, the determinant, the fact that Arling R. Oh, okay. In which case would you have no solutions? When does AX we have no solutions? When I guess the column vector cannot is not in the column space of A. Is not in the column space of A. So more generally, I guess you know that if all the vectors of the matrix A is, there will always be a solution if the matrix, the span of this matrix is always greater than, the span of this matrix is equal to B. Sorry, it's equal to IR of M, where B is M by 1, right? And so for the span of A to be an R of M, there must be at least n different vectors, because you can imagine, you have m different, you call them elementary vectors, but it's like 1, 0, 0, 0, then 0, 1, 0, 0, 0, etc. Right? You need at least m of those. You cannot do better. Yeah. If you want to compute the inverse, that's like one solution. It will have no solution if there's, it can have an infinite amount of solutions, right? If you do compute the inverse, it's not invertible if you have more than one solution, because the inverse is unique, right? So if you have more than one solution, that would be a contradiction. The LP norm. That's the wrong note, bro. Okay, guys, I need to turn on the sports mode because I will go to bed soon. It's almost 2. Holy shit. And I still haven't learned singular value decomposition. Alright. So orthogonal matrices are matrices where the inverse is equal to the transpose. Isn't that... What do I choose? Oh, this is the transpose is equal to the negative. Oh. Such that multiplication I can do. So it's like Okay, they're basically the same. Eigendecomposition. We decompose a matrix into a set of eigenvectors and eigenvalues. The scale of diagonal. Oh my god, this is so cool. What's up? Okay. I'm gonna grind for 10 or 15 more minutes, but we're almost there for a singular value decomposition, and then we can do determinant, and then oh my god. Oh my god, this is great. Wow, that's so much. But I think that this is like fundamental theory that I should be good at. Okay, so singular. I'm gonna call it a night. Good session. I'll see you tomorrow.